As we saw last time, examining an object at the atomic level can reveal its hidden history. Today we will extend this notion to archaeological investigations and show how precise dates can be derived using atomic decay. Carbon-14 has been the primary source of archaeological dating since the technique was invented around 1950. It's something that comes up over and over again in these lectures, and so it's worth making sure we understand this in detail, because it acts as the archetype for all other radioactive dating techniques. Carbon has three naturally occurring isotopes, as I mentioned in the second lecture. The stable isotopes, carbon-12 and carbon-13, make up, respectively, 98.9 and 1.1% of the carbon in the natural world. That is essentially all the carbon. The ratio of protons to neutrons, 6:6 in carbon-12 and 6:7 in carbon-13, are happy. They are stable, and once made, they will not be changed. It's important to emphasize here that when I refer to carbon-12 and carbon-13, I'm really referring to the nuclei of the atoms, not the atoms themselves. Carbon and its multitude of electrons can change partners frequently. Carbon can join up with other molecules, those bonds can break, it can appear in the form of graphite, it can appear in the form of diamonds, it can appear in the form of the carbon dioxide being exhaled by my breath as I speak. So it can take many chemical forms. But the nuclei of the atoms, which were created, as we'll see, in the cores of massive stars billions of years ago, have been unchanged since that time, and the stable isotopes, carbon-12 and carbon-13, will remain so forever into the future. Carbon-14 is a radioactive isotope of carbon with a half-life of 5,730 years, and it represents roughly 1 out of every trillion atoms of carbon in the Earth's atmosphere. So carbon-14 now, again with 6 protons because it's carbon, but with 8 neutrons, is an unstable ratio of protons to neutrons. And it has this convenient timescale for decay of several thousand years, just the kind of timescale we need to date historical and prehistorical events. Now, that's useful for us, but with a half-life of 5,730 years, you might well ask why there's any carbon-14 left at all. 4.5 billion years ago, when the Earth formed, is almost 1 million half-lives ago. And as you recall, the amount of radioactive material left after a certain number of half-lives is 1/2 to that power. So 1/2 to the millionth power is, to a very good approximation, 0. Thus, you might expect that there'd be no carbon-14 left at all, however much there was when the Earth formed. The trick is that carbon-14 is constantly being produced in the atmosphere by the interaction of extremely high-energy particles from space, called cosmic rays, with the very abundant nitrogen atoms in the atmosphere. Exploding stars far across space accelerate particles to very high speeds, very, very close to the speed of light, and they streak through the galaxy. When they collide with something like our planet, they're likely to make a mess, because even though these particles are tiny, electrons or single protons or perhaps helium nuclei, as they come crashing into the atmosphere, every once in a while they'll hit dead on the nucleus of an atom. A cosmic ray hitting a nucleus of nitrogen can rearrange the quarks inside its constituent protons and neutrons and turn one of the protons into a neutron, thus demoting it one step in the periodic table from nitrogen number 7 to carbon number 6, because it's lost a proton, but in the process adding a neutron, making it carbon-14, this unstable arrangement of fundamental particles. All living things are composed of carbon-based molecules. The reason for that is twofold. One is, carbon is the 4th most abundant element in the universe. Helium is 2nd, but it can't make any chemical compounds. Oxygen is 3rd, and it makes a lot of compounds. But carbon is unique for a second reason, and that is that it has 2 electrons in its outermost shell. With 6 electrons in total, shell number 1 has 2, that's its maximum. Subshell number 1 of shell number 2 has 2, and then subshell number 2 of shell number 2 has 2, leaving 4 unoccupied spaces. That means a carbon atom is happier if it joins up with 1 electron atom, 2 electron sharing atom, 3 electron sharing atoms, or even 4 electron sharing atoms. Indeed, carbon likes to link up with itself and makes long chains of molecules. So carbon is a very versatile molecule, and it can be the basis of very complex molecules, the kinds of things we need for life. So its abundance and its chemical ability to share is what makes carbon the basis for life. Plants absorb carbon dioxide, CO2, out of the air through little holes in the bottom of their leaves, through chemical processes cleave off the O2 molecule, breathing that back out into the air, convenient for us, because that's of course what we breathe in, and incorporating the carbon molecule into the structure of the plant. All the carbon in animals ultimately derives from the intake of carbon from plants, because animals lack the clever trick of photosynthesis, being able to take carbon out of the air and incorporate it into organic molecules. Now, isotopes, you will recall, are chemically identical. So all three isotopes of carbon are incorporated into plants in roughly the same proportion as they exist in the air. I say roughly because slight discrepancies amongst the heavier carbon-14 and carbon-13 compared to carbon-12 will become important in our story in a couple of lectures. But for this purpose, it's roughly proportional to their abundance in the air. As a consequence, plants take in mostly carbon-12, about 1% carbon-13, and every once in a rare while, once every trillion times it needs a carbon atom, one of those will be carbon-14. Thus, any organic substance, anything that ever was alive, bones, wood, charcoal, linen, which comes from the flax plant, wool, which comes from a sheep, cotton, which comes from a cotton plant, parchment, which comes from the hide of animals, any of those things that were alive are among the artifacts we can date with this method of carbon-14. Carbon-14 dating relies on the fact that once dead, an organism ceases to incorporate new carbon into its chemical structures. The carbon-12 and the carbon-13 that were ingested during the plant or creature's lifetime remain unchanged. As I said, they're inviolable. The nuclei of those carbon-12 and carbon-13 atoms will never change. But the carbon-14, which are sitting in there amongst the other carbon atoms, starts to decay away. The ratio of carbon-14 to the sum of carbon-12 plus carbon-13, then, declines steadily from the moment of death. Carbon-12, carbon-13 in the denominator are constant, but the carbon-14 slowly decays away, with half of it disappearing in 5,730 years. And so this ratio, carbon-14 to carbon-12 plus 13, gives us a direct determination of the age at which the substance ceased to live, usually within a decade or two, even over tens of thousands of years. Now, after about 10 half-lives or so, the amount of carbon-14 remaining will be so small, less than 1 part in 1,000, which was of what was originally there when it was only 1 in a trillion atoms to start with, that so little is left the method can no longer be used. The oldest dates that have been used then are about 10 half-lives or 57, 60,000 years, something like that. Two methods have been employed to count the number of carbon-14 atoms. When the technique was invented in the 1950s, it originally sufficed to simply monitor a substance, looking for the fast electrons that came flying out of the radioactive beta decay of carbon-14 to nitrogen-14. C14 goes to N14 plus an electron plus the inevitable antineutrino. As one of the neutrons in carbon, which is now out of balance because there's 8 of them to every 6 protons, flips over a quark, turns into a proton, and moves carbon back up 1 step in the periodic table to nitrogen, giving off the negative charge that it needed to do that. So one can just put the sample near a detector that can catch fast, speedy electrons and determine how many decays there are each minute, day, or whatever, and therefore determine the ratio of carbon-14 to carbon-12 plus 13. This method, however, requires quite a few grams of material. How can we know that? Well, let's do a little calculation. Each proton or neutron in an atom is said to have the mass of 1 atomic mass unit. We describe the atomic mass of an atom as equal to the sum of the number of protons plus the number of neutrons. So for carbon, that number is 12. Each atomic mass unit has a mass, if you put it on a scale, a very accurate scale, of 1.67 times 10 to the minus 24 grams. Remember, atoms are really tiny. And so, if each carbon atom weighs 12 of those atomic mass units, 1 gram of that material will contain about 5 times 10 to the 22 atoms, 100 billion trillion atoms. 1 gram. Now, most of those atoms are carbon-12, a few are carbon-13, and 1 out of every trillion is carbon-14. And so to find out how many carbon-14 atoms we have in a typical random sample of carbon atoms, we multiply 5 times 10 to the 22 atoms per gram times 10 to the minus 12, 1 part in a trillion, and we expect 5 times 10 to the 10, or 50 billion, carbon-14 atoms in each gram of pure carbon. Now that sounds like a huge number. You might think it's easy to count them, but again, they're very, very small. Furthermore, they don't decay very rapidly, right? It takes 5,730 years for even half of those to decay. Now the decay rate is not absolutely steady. As you saw in Lecture 5, the decay rate slowly declines continuously over time. But let's just take a rough average. Let's say that half of those atoms decay in the first 5,730 years. There are 3.15 times 10 to the seconds in every year. So if we divide the total number available by 2, half of them decay, and then by the total number of seconds in one half-life, we find out we'd expect something like 0.14, or a tenth of a decay every second. 1 carbon-14 atom decaying every 10 seconds or so. To get an accuracy of 1% on the answer for how many carbon-14 atoms are still present, we need to measure at least 10,000 of these electrons, because a basic law of statistics is that the accuracy of your measurement is represented by the square root of the number of things you count divided by the number of things you count. The square root of 10,000 is 100. 100 over 10,000 is 1/100th, or 1%. So to get an accurate answer, accurate to 1%, we need to sit there and observe and count every electron coming out for about 20 hours, which is a little bit tedious. Furthermore, we don't get every electron, because if we have a sample of carbon, many of the carbon-14s that decay are going to be in the middle of the sample. And inside the sample, the electron may go zipping out, changing the carbon to nitrogen, having undergone the decay, but get absorbed by other atoms, knock other electrons out of other atoms, give up its energy, and never make it out of the sample. So we're not going to get every decay. Thus, it would take days to measure a sample, even grams in size. Often, we don't even have that much material. Thus, a second method has been developed, beginning in the 1960s and perfected by today, called atomic mass spectroscopy, which allows us to separate the carbon isotopes atom by atom into different little buckets, and then just simply count the numbers that are there. So not relying on the decay at all, but actually actively taking the sample and breaking it up into atom by atom and counting the ratio of carbon-14 to carbon-12 plus carbon-13 atoms. Atomic mass spectroscopy works like this. It requires destroying the sample, but it only requires milligrams of material to obtain an accurate date. You take the sample and bombard it either with particles or perhaps a laser beam such that it sprays apart into its constituent atoms. And you hit it hard enough so that not only do the bonds between the atoms in the solid break, but some of the electrons of the carbon atoms are ejected, so the atoms end up positively charged. One then sets up an electric grid with a negative charge over here, attracting all the carbon atoms that are positive to it, and you leave spaces for them to go flying through. Now, each carbon atom, having 6 protons, has the same charge, but the carbon-14 atoms are heavier. The velocity with which the atoms accelerate is proportional to the charge of the atom and the charge on your negative grid over here. And so the acceleration, the force given to all of them is the same. But just like pushing on a bicycle is easier than pushing on an SUV, if you apply the same force, you get much more speed out of the bicycle than you do out of the SUV. And so the heavy molecules, the heavy carbon isotopes rather, move more slowly than the light carbon isotopes. Once you've got them all traveling together in a straight line, you set up a magnetic field. Now, charged particles moving in a magnetic field bend, and the amount by which they bend depends on their velocity. And so what one does is set up the magnetic field, have all these positive charges coming along at different speeds proportional to their mass, Carbon 12 the fastest, carbon 13 next, and carbon 14 slowest. And they come through and they bend and they fall into different buckets. The carbon 12 bucket, the carbon 13 bucket, and the carbon 14 bucket. One then simply counts up the number of atoms once caught in each bucket and gets the ratio we need to determine the age of the substance. Now, two complications must be taken into account in deriving reliable dates from this carbon-14 dating technique. First, one must be certain that no new carbon has been introduced in the material since it died. The key aspect of this technique is that the carbon is being incorporated at a steady rate, at a constant ratio into the material while it's alive, and then when it's dead it stops, the carbon-14 decays away, and the other remains behind. Thus, one wants to be careful, for example, that there aren't bacteria that have been living on a piece of cloth or whatever, which have added active carbon to the material, thus giving you a date that'll be too young because there'll be extra carbon-14 in the substance. The second assumption we must make, and this one we'll examine in detail in the future, is that the rate of carbon-14 production in the atmosphere from these cosmic rays is constant. If it's not, if it's varied, the amount of carbon-14 taken in by a plant will be high when the ratio in the atmosphere is high and low when the ratio in the atmosphere is low. It turns out the carbon-14 production rate does vary slightly, depending on such things as the activity of the sun and the strength of the shielding Earth's magnetic field. It'll be important to take these small corrections into account over time, which we'll do in a subsequent lecture. How do we apply this to actual archaeological sites that we wish to date? Let's start with a water tunnel in Jerusalem that's actually mentioned in the Bible. The Siloam Tunnel carries water from the only permanent spring that exists today and existed 5,000 years ago in the area of Jerusalem into the heart of Old Jerusalem. It's one of the oldest water systems in any city in the world. It's described in the Old Testament as having been built by King Hezekiah, who reigned between 727 and 698 BC. However, the king's name is uncharacteristically missing from the inscription on the monument at the head of the tunnel. This, plus philological arguments concerning the inscription itself, have suggested a date 5 centuries later for the tunnel's construction. An error of 500 years is pretty serious. Standard archaeological techniques could not settle the age of this tunnel. Amos Frumkin and his collaborators in 2003 used a multitude of techniques to derive an accurate date for this tunnel. They drilled small holes through the plaster lining of the tunnel and uncovered a small wood fragment and the remnants of a short-lived plant that were trampled underneath as the plaster was laid down in the original tunnel. Since both these things were alive, the piece of wood and the small plant, carbon-14 dates from atomic mass spectroscopy could be derived. And they were derived with an error of only about 20 years and shown to be consistent with 700 BC. A second dating technique, using the decay of uranium-234 to thorium-230, a pair of characters who will appear again later in our lectures, have dated a stalactite hanging down from a leak in the roof of the tunnel. Now clearly this crack occurred and the stalactite, which comes from the dripping of calcium-rich water down, builds up over centuries. And the age of this stalactite turned out to be 2,320 years, appropriately a couple hundred years after the tunnel's construction, if it were constructed in 700 BC. So the carbon-14 date, the geological data from the uranium-thorium decay, and the biblical written evidence are all consistent with construction in 700 BC, settling the arguments of classical archaeologists. In the 1990s, techniques were developed to use carbon-14 dating on inorganic substances. This was a huge surprise to me. The basis of carbon-14 dating is that something is alive and incorporating carbon-14, and when it dies, there's a particular moment, death, which sets the clock and starts the decay of carbon-14, such that its ratio gives its age. However, clever people have discovered that lime-based plaster, which is certainly not organic and lacks this life-driven incorporation of carbon and clearly lacks the mark of death, can still be carbon-14 dated. Much building plaster is made from limestone. Limestone has the chemical formula calcium carbonate, CaCO3. 1 calcium, 1 carbon, and 3 oxygen atoms. When you heat limestone to 900 degrees Celsius, which is about 1650 degrees Fahrenheit, about the temperature you get if you put a sample in a Bunsen burner flame, you release all of the carbon dioxide, yielding a substance called quicklime. The thing that's left from CaCO3, if you take away CO2, is CaO, calcium and oxygen bonded together, quicklime. In building materials, one takes quicklime and adds water to make calcium hydroxide, CaOH2, that is 2 oxygens, 2 hydrogens, and 1 calcium, or what's commonly called plaster. CO2 from the atmosphere then combines with wet plaster, which releases water vapor to the air, to reform the limestone to make a hard substance again that now binds your bricks or stones or whatever together. The water evaporates into the air, that's an H2O gone. A CO2 is captured from the air, that's a C plus 2 O's added, and one returns to calcium carbonate, CaCO3 again. So, in a sense, plaster is alive in that from the moment you make it wet and stick two things together with it, it starts sucking in carbon dioxide from the air. And as it dries, it stops doing that. That usually takes only a matter of weeks, such that it now has a carbon-14 to carbon-12 ratio, as though it were something that just died, where the carbon-14 gradually decays away and the carbon-12 and 13 remain unchanged. Care must be taken when doing this and using this technique, since the sand or gravel that you mix with plaster to make mortar, which is usually what's used to hold things together, can contain very old carbon that has no carbon-14 at all, which will throw off the ratio. For example, limestone fragments on a beach, which might be scooped up in sand you use to mix with your plaster, might well contain carbon, which is hundreds of millions of years old. Limestone is laid down as tiny little calciferous shells from little creatures in the sea fall to the bottom and get built up, packed under pressure, and then the land, through tectonic activity, the rock comes up onto land, and we see deposits of limestone. That's 100 million years old. There's going to be no carbon-14 whatsoever left in that. And so you will artificially add carbon-12 and carbon-13, that is, add to the denominator, but not add any carbon-14 to the numerator, thus leading to an incorrect date. As in many of these projects, they're interdisciplinary in an interesting way. The team that first perfected the technique of dating drying plaster consisted of a nuclear physicist, a geologist, an art historian, and 2 archaeologists, working together to solve this interesting set of problems. The first one they succeeded at was a stone tower that still stands in Newport, Rhode Island. There are a bunch of people that are very enthusiastic about the Vikings and attribute almost everything that happened in the New World prior to the arrival of the Europeans in the 17th century to the Vikings. In particular, this rather peculiar stone tower was attributed by some to Vikings and therefore thought to be over 1,000 years old. However, using this technique of drilling out small amounts of plaster in the mortar that held the stones together and dating it using carbon-14 decay, it was shown that the tower was built sometime around 1690, completely ruling out a Viking origin. Indeed, it turns out the written record suggests this as well, as this tower is cited as a base of a windmill in Benedict Arnold's great-grandfather's will, but the Viking enthusiasts needed harder evidence to rule out their hypothesis. This group then attacked a problem of great interest, which shows that even in relatively recent times, traditional archaeology can have a big uncertainty as to when structures were built. There are 8 large churches on the Åland Islands of Finland. Åland is a Swedish-speaking island province of Finland that lies rather closer to Sweden than it does to Finland in the Baltic Ocean. It was an important settlement in the Bronze Age when German seal hunters built an oil processing plant there to use seal oil for light and heat. Later, a large Franciscan monastery was established, and large churches were built on 8 different islands. These are important repositories of medieval sculpture and paintings and even some manuscripts, but there is no written document that says when these churches were constructed. Traditional archaeology has led to debates which ranged from 1100 AD rather, to 1490, an uncertainty of almost 500 years, 400 or 500 years, even only 600 years ago. This is a measure of the imprecision of classical archaeological and art historical techniques in dating buildings such as this. So, our atomic historians to the rescue. On the island of Kokar, where the largest of these churches is, they sampled the plaster and attempt to derive a date. Now, it turns out they were lucky, because on this island, the beach sand contains no limestone whatsoever, only things like silicon dioxide, which they mixed with the lime to make the mortar that held the stones together. So there was no contamination from limestone. Subsequently, they found on other islands where glacial deposits of limestone had been laid down on the beaches, their technique did not work as well. But on Kokar, there was only quartz and feldspar and sand and no old carbon. And so they derived a date for the church. In addition, they used another technique, which we'll discuss in a subsequent lecture, counting the tree rings in the roof beams of the church. One of the beams, which gives a very precise date because we can match the thicknesses of the rings exactly as I'll show, gave the date of 1281 AD. The mortar dating came in with a date between 1279 and 1290, a perfect match, accurate to 10 years, showing that these churches were indeed much older than some archaeologists had suspected. Confirmation of this technique was done with a third technique called thermoluminescence, an examination of the roof tiles for a peculiar light that's emitted when things like ceramics are heated. When you have something like a volcanic lava or a ceramic pot or roof tile that's been heated up to high temperatures, all of the imperfections in the crystals get wiped out, and the crystal is relatively perfect when it cools. However, as cosmic rays, the same ones that make carbon-14, come charging in through the atmosphere and slam into these materials, they can create defects in the crystals, knocking electrons out of where they should be and trapping them in other imperfections in the crystals, so they're not where they belong, leaving charged particles, both positive and negative, behind. These trappings are really severe. The electron can be stuck there for something like 100,000 years. Now, the number of trapped electrons in this state is proportional to the length of time that the object has been exposed to cosmic rays since it was zeroed out by firing the tile. If you heat the sample slowly, you can liberate those trapped electrons, have them hop back over the lattice and jump into where they belong. And when, as we've seen, an electron joins an atom and jumps down its energy levels, light is emitted. The amount of light given off is proportional to the exposure that the substance has received, and thus to its age. Careful calibration of the technique is essential. One needs to know how many trapping sites there are and how readily they're filled with electrons. And this is done after the thermoluminescence is recorded by exposing the object to artificial neutron bombardment and then calculating the trapping efficiency. The Roman amphitheater in Merida in Spain was dated to 100 AD using this technique, a century later than the written inscription at the entrance to the theater. However, consistent with it being a copy of the Roman Colosseum, which it was architecturally, thus it was surprising that the inscription suggested it was built first. In fact, carbon-14 dating of the mortar showed that it was built after the original Colosseum in Rome. The date for major construction on the elaborate villas of northern Portugal were found to be 580 AD, a century and a half after the collapse of the Roman Empire, showing that Roman technology in building, in waterworks, and in other things survived long after the collapse of the empire. In several of these examples, the date measured using atoms helped to redefine history. The concept that the atoms incorporated into a substance can help reveal its history is a powerful notion that we will use repeatedly throughout this course. Next time, we will apply it to ourselves, since, atomically speaking, we are what we eat.